Okay, let's start chapter 4. So an interesting, just to review here, we've talked about relations. I hope you don't forget what they are. They are literally the easiest definition in all of math. And the definition of a relation is a set of ordered pairs. Really simple. And as it turns out, some types of relations are functions. And remember what a function is? Basically, the graph of a function passes the vertical line test. No two domain values are ever repeated in the set of ordered pairs. And now we're going to look at a special type of functions called one-to-one functions. So, just to give you the bigger overview, drawing a little bit better of a graphic here. So, the circle is going to be my set, and that set is going to be the set of all relations. For some reason that doesn't look right to me, because it's not right. And inside this set is another set, and that is my set of functions. So every function is a relation. And one last one, inside the set of functions, I have more than one. I have the set of one-to-one functions. So every one-to-one function is a function, and every function is a relation. So there are two ways to determine whether a function is one-to-one. Actually, there's going to be more than two ways. But the first way that we always give you in mathematics is the definition. So here is the definition, if I can make it appear. So this is the formal definition. So we start out with a function. So this you assume I'm giving you a function. So you've been given a function. The question is this function you've given me one-to-one or not? So a function f is a one-to-one function if for each element a and b in the domain of f, as long as a is not equal to b, then f of a is not equal to f of b. So a better, and I think, way to say that, it's an equivalent way, is to say whenever fa is equal to f of b, then a is equal to b. And I'm going to go ahead right off now, and I'm going to give you a visual definition of this. We will give a visual test for one-to-oneness soon. But right now, we've got just the definition, the abstract definition. So here are two Cartesian coordinates. I'm going to draw a function like a parabola. That's definitely a function. And then over here, maybe I should have used a different color. I didn't think that far in advance. I'm going to draw another function. I mean, when I say draw, I mean I'm drawing their graph. And this is just the graph. So let's choose two arbitrary domain elements. Right here will be A, and right here will be B. Same over here. Here is A, and here is B. So that's A and B. So clearly we have that A is not, not equal to b, because there are two different points on the number line. So now we have to check, what about f of a, and how does it compare to f of b? Well, once you've been given a and b, on the number line, how do you find f or a or f of b? Well, we go straight up until we hit the related point on our graph. And then I come straight over. And this point on the number line here, maybe I'll use reddish, is my value f of b. And ditto down here, I've hit the graph. I've gone straight up perpendicular from the x-axis until I intersect the graph of our function. And then I go either right or left. In this case, it's right, until I intersect the y-axis. And that point of intersection right there is my value of f and b. And clearly, my value of, sorry, I said f of b, that's my value f of a. So clearly, my value of f of a is not equal to f of b, and this will be always the case whenever I choose an a which is not equal to b. But let's do the same thing over here. This is some quadratic function. So here's my a. So what do? Is I go down and I find where it intersects. Then I move over, and that point right there is my f of a. And here is b. I come down. I did not draw this perfect, but when I move it over, it's going to hit the same thing as f of a. So in this case, we have a not equaling to b, but f of a is equal to f of b. So this function, this linear function, is 1, 2, 1. This function, which is not linear, is not 1, 2, 1. So if you're excited by a graphical test to determine one-to-one functions, you will be getting one. So for the first thing we're going to do here is let's determine by just algebraic methods, no graph, whether these following functions are one-to-one. So we won't do the graph, we'll literally just use the definition. So my function here is f of x is equal to minus 4x plus 12. So let's assume that we'll use this particular, that f of a is equal to f of b. And what we want to show is this means that a is equal to b. So what I'm doing here is we're going to use the equivalent way. We assume that f of a is equal to f of b, and then show that that assumption leads to the conclusion that a is equal to b. So let's do that. So f of a, let's find out what f of a is. F of a, what do? We just replace the x value with a value of a. And f of b is equal to minus 4b plus 12. So let's assume that f of a, let's do step one. Let's assume that f of a, so this is what we're assuming. We don't have to give any reasons for it, we're just assuming it. So we're assuming f of a is equal to f of b. That means minus 4a plus 12 is equal to minus 4b plus 12. So now we want to show that that assumption leads to this conclusion, that a is equal to b. Well, what are we going to do? We're going to isolate a and b. So I'm going to subtract 12 from both sides. That gives me 4a is equal to minus 4b. And now I'm going to divide both sides by minus 4, so the equality remains. So that gives me, as my last step, that a is equal to b. So we assumed that f of a was equal to b, and that gets us this first step right here. Then we just do some algebra, some just regular algebra. And the final step is that a is actually equal to b. So this function, f of x, is 1, 2, 1. Now let's do the same thing for b. So f of x is equal to the square root of 25 minus x squared. And remember, remember what its graph looks like. This is always the positive branch, or the positive part of the graph. So its graph is going to look something like this. And this point right here is going to be 5, 0. But what about the other side of the graph? What about minus 5 and 0? I'm going to have something that goes like that. So that's just kind of what the graph looks like. It's kind of helpful sometimes. But let's go ahead and approve this algebraically. We're going to assume f of a is equal to f of b. And then we want to show that means a is equal to b. So f of a is equal to the square root of 25 minus a squared. And f of b is equal to the square root of 25 minus b squared. So let's assume both of these are equal. That's our first step. So I set both equal. And then I solve for b on both sides. I want a on one side and b on the other. So I'm going to square both sides. So by squaring both sides, any original solution is maintained, but I might get some extra solutions. So that's going to give me 25 minus a squared is equal to 25 minus b squared. So I'm going to subtract 25 from both sides. That's going to give me minus a squared is equal to minus b squared. Then I'm going to multiply both sides by minus 1. So minus 1 multiplied by both sides gives me a squared is equal to b squared. So the question is, I've got to solve for a. So when I take the square root of a squared, that's going to give me, by the square root principle, plus or minus the square root of b squared. So that means a is equal to plus or minus b. In other words, for every a, there's two b's that work. I'll give you an example. 25 minus, let's not go back to the original equation, let's just start with here. Let's just show right here that if a squared is equal to b squared, does not mean that a is equal to b. Does not mean this. This is going to be, that's what we wanted to show, but it's not justified. So, by means of example, let a equal 4 and let b equal minus 4. Then clearly, a is not equal to b, but a squared is equal to 16, which is equal to minus 4 squared, which is equal to 16. So this particular function, the conclusion is this particular function is not 1, 2, 1. And we can actually, if we come over here, we can actually see that on the graph. And that's going to be one of the niceties of this particular type of, this graph is not the best in the world. I don't even need to do that. Let's just look at this line right here, where a is equal to minus 5 and b is equal to 5. Then the corresponding point, f of x, is equal to 0. So you can see right there from the graph that it's not 1 to 1. So that's what I'm going to introduce you to in the very next page. So it's the horizontal line test. So a function f is 1 to 1 if any horizontal line intersects the graph of the function just once. So remember, we don't have to do the vertical line test. I'm already giving you a function, so you know it passes the vertical line test. So we can do another line test, a horizontal line test. And if I draw a horizontal line, and if it's true that no matter where that horizontal line is drawn, it will only intersect the graph of the function once, then the resulting function is 1 to 1. So let's look at some examples here. Clearly, this will not pass the vertical line test, the horizontal line test. If we just look at this line, y is equal to minus 1, it's going to intercept the graph 1, 2, 3 times. So the function f is not 1 to 1. But if I look over here at this linear function, this is the graph of a line with the negative slope. No matter where I draw my horizontal line, it's only going to intersect the graph of that function once. So function g is 1 to 1. So f is not 1 to 1, g is. So that makes it a lot easier. If you can graph a function, then you can know just by looking at the graph whether it's 1 to 1 or not, and you don't have to do an algebraic test. Sorry, my voice is weak. I realize I have a weak voice the older I get. And today's particularly weak, and I don't know why, but just bear with me. So a new way to check to see if a function is one-to-one. So the first thing I'm going to do is I want to talk to you about, I say recall. When we say recall in math, that means we've already discussed it and you're supposed to know it. And I know that's not the case. So a function f increases over an open interval if two elements of the domain, a and b, where a is less than b, means the value of the function at a is less than the value of the function at b. So let's take a visual look at this. And we're going to use the easiest of examples. We're going to use a linear function. So let's look at our two examples. So let's find an a. Let's identify an a that is less than b. So we'll consider this open interval right here. This open interval. So we'll call this, if you want that to be 10 and this minus 3, our open interval would be minus 3 and 10. But we could just consider the open interval of the entire line minus infinity to infinity. And that would work in this case. So here's a. Let's find, go straight up. And that's the point a, f of a. So right over here is my point f of a. And here's my b. I'm going to go straight up. There's the point b, and f of b. And then I'm going to come over here, about right there. I'm going to say that's f of b. So down here we clearly have that a is less than b. And what do we have up here? We have that f of a is less than f of b. So if this is true, then this is also true. So that means this particular function, this linear function with positive slope, is increasing. And in this case, we know it's increasing over the closed interval minus 3 and 10. But it doesn't matter where I put the closed interval. This would be the case no matter where I put my a and my b on the number line. As long as a is less than b, I'm going to have f of a less than f of b. Let's do another example. Another visual example. This time again it'll be an easy visual example. Not the best draw in the world, but well, I could actually do this. Let's do this. Let's take an actual graph. This is a good one. So I'm going to make it bigger. And I'm going to take a screenshot. Might as well use technology when we have it. So here we go. So right here is my function. So if we just look at this, and remember when you have functions like this, when they don't show you the end, you just assume it keeps on going in this direction forever. It goes down off to the bottom left forever. And up here, it goes off to the top right forever. So let's take a look at this. By its graph, I would say that the function, we have to decide what that value is right here. And I'm just going to pretend it's 0.8. It's 8/10. It's between 0 and 1. It's greater than 1/2. And maybe it's closer to 0.75, but 0.8 is easier to draw. So I would suggest by the graph, the function is increasing. Now remember, these are increasing over open intervals from -infinity to the point 0.8. It's increasing. So remember, when you're thinking about increasing, you're thinking about walking from left to right. Are you going uphill? You're walking on the graph. Are you going uphill or are you going downhill? So it's increasing from -infinity to 0.8. And then we start going downhill again. So we have to decide what this value is right here. So let's say we'll say this is about 2.25. So it is decreasing over the open interval. So these are always open intervals, 0.8 to 2.25. And then it starts to increase again. And it increases all the way from 2.25 to infinity. So we've looked at increasing functions. Let's look at two function values for decreasing. So here's going to be my A, and here's going to be my B. I'm going to come down here, so I have A is less than B. So let's go down and I find my value here. So that's the point A, f of A. And down here, this is going to be the point B, f of B. So over here is going to be my f of A value. And down here is going to be my f of B value. So I have A less than B, but f of B is less than f of A, because this is negative, so f of B down here is more negative than f of A. So f of B is less than f of A. So that's an example of the exact same definition I gave you for increasing, modified to deal with decreasing functions. So right here is that little spiel. If A is less than B, implies f of A is greater than f of B. So here is our theorem. So this is a really cool theorem. It's another way that you can tell if a function is one-to-one. So if a function f increases or decreases over its entire domain, all of it, then that function is a one-to-one function. So an example of a function that decreases over its entire domain is any line with negative slope. A function which increases over its entire domain is any line with positive slope. Can you give me another example of a nonlinear function for which this is true? Let's take a look. So we have y is equal to, it's the easiest of all linear functions, y is equal to x. That's increasing over its entire domain. What is the thing about the polynomial on the right? It's a degree 1 polynomial. It's an odd degree. Let's try degree 3 polynomial, the next odd degree, x cubed. Turn off my other one. It is also always increasing. If I zoom in right here, it seems like it goes flat, but it doesn't. It always is increasing. Let's try another one. Y is equal to x to the 5th. And you should have anticipated that that is also an increasing function. So that'll be something we look at later on, is whether we can tell whether a function is increasing or decreasing just by looking at its graph. Well, looking at its graph in our heads, looking at its overall degree. So it says, look at the graph of the functions g and f on page 2 and verify that g satisfies the increasing function theorem and that for f there is at least one turning point. So here is this word turning point. And I'm not for sure whether I defined a turning point for you or not. Normally I do, but I don't think it's included in the actual concepts that you are given. So here's a turning point. It's really, really simple. So here we have a function. It's increasing. Then it starts to decrease. Then it starts to increase. Well, the point where it changes from increasing to decreasing or decreasing to increasing is called a turning point. And there's a turning point theorem. Now, I just gave you the exam on chapter 3, and the scores weren't very good. And that's probably because this is being done remotely rather than in the classroom. And that brings a lot of difficulties in learning. So I chose not to go into further detail in chapter 3 by discussing turning points and turning point theorems. But that's a turning point. If I were to draw another function right here, that would be a turning point, say. That would be another turning point. That would be a turning point. And that would be a turning point. So visually, they're pretty easy to detect. So let's look at the graphs of the functions g and f and verify that g satisfies the increasing function theorem and that for f, there is at least one turning point. So, and we just did that. I just showed you and defined turning points for the very first function. So that kind of leads to the following observation. If the graph of a function has a turning point, just one, that means it's not an increasing function. And indeed, I give you a corollary. And this is the corollary right here. So the increasing function theorem is right here. If a function f increases or decreases over its entire domain, then f is 1 to 1. So a corollary is a really easy theorem that follows from another theorem. If a function is not 1 to 1, so then there exists some open interval of its domain that is not increasing or decreasing. So that means, by what we just said, there's got to be some turning point. So mathematical reasoning, I just did it for you there. You use the corollary of 2 to give reasons why if a function is not 1 to 1, then it has to have two turning points. And here I'm talking about two roots. If you have two roots, that means two places where a graph crosses the x-axis. There has to be at least one turning point in between them. So I'm going to kind of skip that one because we didn't go into turning points, and the theorems and the corollary there's you don't have to worry too much about. The only thing that I want you to know is this one right here. If a function f increases or decreases over its entire domain, then it's a one-to-one function. And if it is not a one-to-one function, there has to be some open interval of its domain where it's not increasing or decreasing. So it could be constant over that interval, or it could have a turning point. Those are the two. So we have this concept of an inverse function. So let f be a one-to-one function. So now you're given two things. I've given you a function f, and I've also told you it's a one-to-one function, so you don't have to verify that. So if you know that your function is a function and that it's one-to-one, then g is the inverse of f. So a new function g is the inverse of the function I just gave you if both of the following conditions hold. F composed of g of x is equal to x for all x in the domain of g, and if g composed of f of x is also equal to x for all x in the domain of f. So another way of saying this is that, remember, let me bring up my board here. Another way of writing f composed of g of x is f whose input is g evaluated at x. So another way of saying this is f of g of x is the identity function. That means for every input, I get the exact same output. If 7 is my input, the output is 7. If minus pi is my input, the output is minus pi. And this is ditto. It works the other way around. It has to work both ways. G composed of f of x. That's another way to write that is the function g with f of x as my input. So if for all x in the domain of g, f of g of x is equal to x, and for all x in the domain of, this is f composed of g, and this is actually g composed of f, sorry, of already f composed of, this is f composed of g, and this is g composed of f. We have g of f of x equals x. Then we say g is the inverse of f. So remember that f doesn't necessarily have to be a one-to-one function. As it turns out, if f is not a one-to-one function, then f does not have an inverse. And every one-to-one function does have an inverse. So let's take an algebraic look. I know a lot of this is, again, conceptual, and you've been spending all of your mathematical life playing with x's and y's and solving and raising powers. And then we start at some point in college algebra is literally where it really starts. We start really putting the spotlight not on the manipulation of symbols, but up on the manipulation and examination, intellectual examination of mathematical concepts. And they're abstract. And it's the first steps on the road to really abstract reasoning. It's a beautiful road. It leads to something more beautiful than what is it they get to at the end of the freaking Dorothy and the Wizard of Oz, the Emerald City. This road leads to very, very beautiful things in mathematics. And we're starting you on it in this class. And that's the reason there's all these big, long, text boxes like here with a lot of conceptual information and definitions. And really, we spend most of our time talking about this and very little about this. So here we have an example. And what we're supposed to do is to show that G is the inverse of F. So here's how we go. Let X be in the domain of G. Now I actually think that we can loosen the restriction. Normally we would say let F be in the domain of F composed of G. But since we're restricting these to inverse functions, I think I've got to go through the proof, but I think we can literally just pretend that X is in the domain of G and not worry about whether it's in the domain of F composed of G, because if G is an inverse of F, then it obviously will be in the domain of F composed of G. Then we want to show that F composed of G of X is equal to X. So that's part one. And part two is let X be in the domain of F. Then we want to show G composed of F of X is equal to X. So I'm going to give you, this is what we want to show. So this is what we assume. And this is what we want to show. And here, so that second part, we assume this. And this is what we want to show. This we want to show is so important in higher mathematics. We often abbreviate it WWTS. We want to show. So again, we're conceptually doing this. So let's go ahead and do part one, and then we'll do part two. So here it goes. So let X be in the domain of G of X, which is equal to the cube root of X plus 1. Now, I don't have to say anything about what that domain is. I'm just saying, whatever that domain is, let's just suppose it's my value that I've chosen, X, is in that domain. So that's what we're going to assume. So I want to show that F of G of X is equal to X. So this is my assume. And this is what we want to show. So let's go ahead. I keep looking up at the clock because I have another exam getting ready to start here very soon, and that maybe students saying, "Where are you? I'm here early." So after I do this particular problem, I'll pause it and I'll finish the rest after I give the exam. So let's find out what is f of g of x. So f, remember, f is equal to x cubed minus 1. So f of g of x is equal to f of the cube root of x plus 1. So that's my input, which is equal to my input value, which is the cube root of x plus 1, is cubed. And then I subtract 1 from it. That's what f does. So the cube root of x plus 1 cubed is just x plus 1. And then I'm subtracting 1 from it, and that gives me x. So I showed that f of g of x is equal to x. But I'm not quite done. I have to do part 2. Now let x be in the domain of f this time, where f of x is equal to x cubed minus 1. So we want to show g of f of x is equal to x. Well, g is going to take the input f of x. It's going to take his input x cubed minus 1. So that's the same as cube root. Now I replace my x value with all of this, x cubed minus 1, and then I add 1 to it. So remember, this is my input, x cubed minus 1, and that's my input for g. So that's equal to the cube root of x cubed. X cubed is itself a increasing function. The cube root of x cubed is x. So I just showed that hence we would say g of f of x is equal to x. And our final conclusion is that f as given above and g are, here is the term, inverse functions. And when that's the case, we usually rename, because these names are arbitrary, right? G as f inverse. That's read as f inverse. The minus 1 hasn't got anything to do with raising a function to the minus value, to the minus 1 exponent. It just means it's the inverse. So we rename g as f, and f of f. And we have the following. I got somebody at my door. Sorry about the interruption. So let's move on. And here we have, it looks difficult, but it's really not. So the takeaway is we're given a function f that has an inverse. So that's important. If x, where is my, okay, here we go. If x, f of x, is a point on the graph of f, then you can You don't have to deal with this, but the onset is f of x. X is a point on the graph of f inverse. Now, if some of you are students who have to have everything, you have to go through everything logically for it to stick, and I was one of those students, then to understand what I did right here, basically I just took the function f of x, I just took the function value of both of these things by f inverse of x. And to understand it, you can go back to where I give the definition on page 4 of the inverse function. I have a feeling most of you are fine to take it on just me saying so. But the point about it is this right here. If a comma b is the point of the graph of f, and f has an inverse function, then b comma a is a point on the graph of f. So let's look at that visually. So here's some graphs I took from the book. So right here in blue is a linear function with positive slope. So it has inverse because it is always increasing. So let 3 comma 1 be a point on the graph of f. Now we know f inverse exists, and I can find a point on f inverse by just switching the places. 3 comma 1 becomes 1 comma 3, and right there is a point. Here down here is another point, the x-intercept of the blue linear function f, and that's minus 4, 0. Well, I can find another point on f inverse by just switching the values to 0 comma minus 4. Now I have 2 points, and once I have those 2 points that lie on the graph of f inverse, I can graph them. Notice this dotted line right here. It's the equation y is equal to x, the identity equation. And you'll notice that if we folded the equation of f, if you go through what it means for a function to be reflected across a line, then you'll see that f is the reflection of f inverse across the dotted line, and ditto, f inverse is the reflection of f. Over here we have another example, but it's not linear. We have, this looks like a quadratic function with restricted domain. And if I look at its inverse, since its domain is restricted, we can actually make it into an always increasing function. We can see that a point 1, 1 lies on both of them. And then the point on f that is 2, 4 lies on the point 4, 2 of f. And again, it's a reflection across this dotted line, which f of x is equal to x, or y is equal to x. Remember, f of x and y is the same. So here is the thing. Normally, a degree 2 polynomial does not have an inverse. Remember, it's a parabola, and it would not pass the horizontal line test. But if we restrict its domain, suddenly it can have an inverse. So let the domain of f of x be 0 to infinity. Let the domain of f of x, which is equal to x squared minus 5, be 0 to infinity. I've restricted the domain. Use a table of values to plot at least 5 points on f, and then use the above to find the corresponding points of f inverse. So again, remember, in general, a degree 2 polynomial, the domain is minus infinity to infinity. If we include that domain here, then it doesn't have an inverse because it doesn't pass the horizontal line test. But by restricting the domain, we can make it pass. We can make it an increasing function and pass the vertical line test, and hence make it have an inverse. So this is a good example. So let's take this screenshot and let's do this. That'll do. So let's look at the points. So we're just going to plot. Say plot at least 5 points. That won't be hard. Although my graphing area may not be enough to get all points on this particular graph, we'll just plot the ones that we have. So this is going to be x, and this is going to be f of x, which is equal to x squared minus 5. Now remember, the domain is given to be 0 to infinity. So my x values are taken from that domain. So 0 is included, so I'm going to grab 0, 1, 2, 3, and 4. There's 5 values. So 0 squared minus 5 is minus 5. If x is 1, 1 squared minus 5 is 1 minus 5, which is minus 4. If x is equal to 2, 2 squared is 4, and 4 minus 5 is minus 1. If x is equal to 3, 3 squared is 9, and 9 minus 5 is 4. If x is equal to 4, 4 squared is 16, and 16 minus 5 is 11. So let's plot these. 0, x is 0, and y is minus 5. So the y-intercept. Then 1 and minus 4. Then 2 and minus 1. Then 3 and 4, and then 4 and 11. So you can kind of see that's a parabola. If I can kind of try to sketch it. See what happens. Okay, people, don't laugh. I know you're laughing. I'm laughing. I'm erasing it. It's really bad. You can imagine what it looks like. It's just using my apparatus here. It doesn't work very well. So now let's look at x and the inverse of f. Again, it has an inverse. Why? Because we've restricted its domain. The point being is, I don't have to figure out what f inverse is. I just switch the value. So in my first row, instead of 0 minus 5, I have minus 5 and 0. Instead of 1 minus 4, I have minus 4 and 1. Instead of 2 and minus 1, I have minus 1 and 2. Instead of 3 and 4, I have 4 and 3. Instead of 4 and 11, I have 11 and 4. So let's plot these. Minus 5 and 0, right there. Minus 4 and 1, right there. 1 and minus 2, minus 1 and 2, sorry, right there. 4 and 3, right there. 11 and 4, right there. So let's take a look at what, I'll use GeoGebra so we can actually see what that looks like. But let's actually find the inverse of this so we can use GeoGebra. So f of x is given for x squared minus 5 for x in this restricted domain. So we're going to find the inverse. Y is equal to x squared minus 5. Switch. X is equal to y squared minus 5. We solve for y. We add 5 to each side. And then x plus 5, we take the positive square root, is equal to y. So remember, the domain of f is that. Let's see what the range is. The range of f is, if we go back up here and we look, our range starts at -5 and goes to infinity. We'll see it a little bit better when I plot it. So our range, it starts with and includes -5 and goes to infinity. So f inverse of x is equal to the square root of x plus 5. Its domain is the range of f. So that's equal to -5 included to infinity. And its range is the same as the domain of x, which is equal to 0 to infinity. So you figure out two things. You just flip them around, and you get the answers to the domain and the range of its inverse. So let's go to GeoGebra, and we'll take a look. So it was x squared minus 5. Now, not that. The problem is here is literally all we have to look at, all we can look at is this side, okay? So we're ignoring anything on the left-hand side of the y-axis. I really don't know how to range domain restrict in GeoGebra. I should have looked it up. And then we're going to do x plus 5 raised to the 1/2. Now here, again, just ignore all of this right here and just focus on this part right here and then this part right here, and those are the inverse functions. And we'll look at y is equal to x, and there is the symmetry for x greater than -5. Would that work? Nope, that doesn't work. I don't know how to do it, but you can kind of use your own imagination and see. So here's some facts about inverses, and this is from our earlier observation. If f is 1 to 1, then f inverse exists. So f is 1 to 1. What's another way we can tell if f is 1 to 1? F is increasing over all of its domain or decreasing over all of its domain. If that's so, then f inverse exists. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. If AB lies on the graph of f, then BA lies on the graph of f inverse. And the graphs of f and f inverses are reflections of each other across the line y is equal to x. So we actually have already done example 8. If you look, you'll find that wrong screen. Although I should probably deal with that screen. You will find that f inverse was x plus 5, and hence if f is x plus 5, its inverse is x squared minus 5. And we found the domain and the range. Now this is a bonus, and what I will do is I will make a video all by itself on this bonus little fun exercise when we use encoding methods to code a secret message. I've encoded a secret message for you, and you get to find the inverse of this function and decode it, but I'll make it a special video just for that.